Thank you. So contrary to the two prior speakers, I will not show any formula. It's getting worse. I actually have no results to show. This is all anticipation, and obviously, since this hopefully helps the community, I was invited here to tell you what we're planning to do. So no formula, no results, just promises. So let me give you a little bit of a background here. I am from the semiconductor industry, so optics is not necessarily something that I've grown up with, even though I have a degree in physics. The semiconductor industry has driven a tremendous productivity improvement. I mean, I assume every one of you has one or maybe several of these, but if you had to buy one of these things maybe like 25 years ago, you would have to be a billionaire to afford one if we had been able to build them. So traditionally, the semiconductor industry has provided productivity enhancements in the order of 25% of cost takedown per year, which again gets this multi-billion-dollar gizmo into your pocket for $400 or $500 or whatever you're willing to shell out if you are into Apple. This concept, I guess some call it a law, and we'll get to that on the next page, is still going on, but it has taken a somewhat different shape now. So as you see on the top left there, this is a chart from Intel. It still says that the cost per transistor is going down from generation to generation. That tends to be a little misleading because the generations have started to space out more. So you see that on the left bottom chart. There's a clear and distinct kink in this curve, and it had a lot to do with how difficult it has become for us to continue to scale down from litho generation to litho generation. And the main culprit of that is, the litho equipment that we're using has not changed wavelength for about 15 or 20 years, and that's obviously a problem. Despite all the advances that we can make with potential resolution enhancement, it comes at a cost. And it's cost that's slowing this curve down. Now, if I wanted to take that and look at the system level, maybe there is a kink in that curve, but it really isn't very pronounced, whereas the kink in the introduction of these generations is much more pronounced. So the point of this is that people have learned what to do at a system level. So while we have had sort of a stop in litho introductions for the last 15 years, we have had innovation take place at other stages in the system. So here's one of the things. I mean, most of you have heard about Moore's Law. I mean, this is sort of what I've been talking about. It's not a law. If anything, it's a financial statement. As I said, cost is being taken out of the system by hook or by crook every one of these generations. But in the last few years, again, because the complexity of scaling has taken such a financial aspect to it, very few companies are really still in that space of leading edge CMOS development. And the main things that are holding us back to this point is that every new generation we come up with a new set of materials, novel device architecture. People are even talking about replacing CMOS, although I'm quite pessimistic that that's realistic. But there's this other area that has really evolved, which now is breathing life into the more sort of mature semiconductor users that aren't necessarily at the leading edge. And in this case here, I want to make the point at the bridge to photonics. People have suddenly recognized that the bandwidths of a system can be changed dramatically if you get away from wires and getting information through a wire, but instead using a fiber. Now, the concept of this whole thing, you scale this thing down. Ideally, you bring it eventually onto a chip, and you can really revolutionize the way information is being used. And there's a green angle to this, of course, as well, because transmitting a photon costs a lot less energy than pushing a current through a wire, especially if that wire is long. So the concept was, can you take what we've learned in the semiconductor industry with all the infrastructure that's being put in place, and can you apply that to the photonics or the optics industry? Give you a little bit of a background here. Of course, people are now in 300 millimeter wafers. This is about, a wafer this big. And the transition happened about 15 years ago, 10, 15 years ago. And it was done for cost reasons. I mean, whenever you go to a larger wafer size, the cost of making an individual wafer goes up, but not by much, whereas you gain on the area side by a factor of 2.2 or so. And therefore, for companies like Intel, and like Global Foundries, TSMC, and others, this makes sense, so they have migrated. So did all the key equipment suppliers. I mean, all these companies like Applied Materials, Lam, ASML are producing tools at the leading edge. And you will find that if you're on the lagging edge, that you don't get access to the latest and greatest of technology as easily, nor do you get the same level of maturity or capability of these tools. There's a packaging and test supply chain, very distinct in the semiconductor area. There are things that would, attract a lot of scientists, multi-project wafer runs, coordinated by entities that have sprung up again in the order of 15 years ago, like Moses, for example, that coordinates the input from universities, aggregates them, and then sends them to a foundry like a TSMC or Global Foundries, so you can get your stuff done cheap, right? Which is, more compatible with the financial constraints of most universities. And of course, we have had consortia and road mapping activity. The ITRS roadmap has been around for a long time. I mentioned two consortia here. One is G450C, the other one is Sematech, both of which are at SUNY Poly in Albany. And if you really look very, very carefully there, I picked that, of course, for a reason. That picture shows me holding a 7-nanometer chip wafer. And I got a lot of grief for that because I'm usually never in the clean room, so they asked me if I got lost, right? So about 6-7 months ago, we were announced. The manufacturing institutes, I now need to spend at least a little bit of time here explaining. This is a concept that, of course, originates ultimately with President Obama. There are now 7 or 8 of these institutes that have been announced. There was one announced within less than a month after we were announced. But all of these are meant to focus on manufacturing technology. So it's not science, sorry. It is manufacturing technology. It's what we can do, and it is focused, in our case, obviously, on the US industry primarily. But what can we do to help industry bridge that gap? I mean, some people like to call this the valley of death, where universities make an investment here, and then industry picks up much later. And this valley in there is really representative of, unfortunately, the lack of what used to be in existence 25, 30 years ago, the large industrial research labs that published and filled that space to some degree. Now, other things have to be put in there to enable this transition, because otherwise all these neat ideas never make it into production. So here's also one chart that I absolutely need to show. I mean, clearly, while we won this consortium proposal, this was, the result of a lot of groundwork, and I'm very clearly here, paying homage to Tom and Alan that have been very instrumental over a number of years to prepare the ground for integrated photonics, in particular, to be one of these NNMIs. So what's the challenge here? I mean, I just made the point that the semiconductor industry in principle can contribute a lot to this industry here as well, but it's not quite the same thing. I mean, I'm showing one of these structures that we are building in SUNY Poly, and if you are a semiconductor guy, I mean, you shudder, because everything in semiconductors is rectangular. I mean, there's just, and it's highly, especially if you get into the more advanced CMOS nodes, it's very regimented of how you need to design these things. So to put round stuff on a wafer is something that most people in the semiconductor industry, shy away from. And it does require a complete rethinking of how you do these things. I mean, we're using state-of-the-art semiconductor tools to build these things, but certain things that people do in the semiconductor industry, like optical proximity correction, actually hurt you. So we had to learn of how to do without or do better in accommodating this. So these processes are non-standard. There's a need to integrate optically active materials. Now, here's the problem with the semiconductor line. I mean, optically active materials are different, obviously. I mean, you have to grow these if you want to, on a silicon substrate. There's a lattice mismatch, creates defects, not good. On top of that, most of these materials are different enough that they impact subsequent or previous semiconductor processes if they contaminate your equipment. So you have to be very, very careful that you're not bringing down the line by introducing materials like that then get the contamination spread across the line. We do have a manufacturing line, so it is something that is being taken very, very seriously here. The infrastructure in photonics is immature. I hope I'm not insulting anybody here, but compared to what you can do on the semiconductor side of things, it is really quite nowhere at the moment. And on top of that, in the US, there's really no open access validation and production capability. So for the universities here, I mean, you have to rely on your own labs, and there's no such thing as a Moses that can, do a little run. Or there was an attempt, but it didn't go anywhere because, the financial circulation ultimately did not work out. Now, there's one other point at the bottom of this, and I'm getting to that here on the next page. I mean, our facility in Albany can take us beyond what the original intent of the NNMI was. So let me show you this. Again, please remember this is a manufacturing institute, so we're really supposed to look at manufacturing technologies. And the range that the original intent of the NNMIs is that it's between MRL4, which is basically saying, well, we have identified a process, and it's going all the way through MRL7, which allows you to build prototypes. The SUNY Poly facility can go further than that. So we can certainly go through MRL8 and even partially into MRL9, so we can do small-scale production runs. It is a development line, so I don't intend to, nor do I have the ability to compete with industry. That's not the intent. But it is interesting to note that this is helpful because a company that comes up with a process that has a relatively low volume would still not be very welcome in a large-scale semiconductor facility because it's disruptive. So once you have a certain volume, a large manufacturing entity will be welcoming this sort of project, but you have to get it to that point. So the capability here of going to MRL 8 and 9 is welcome from the industry. Again, I'm not trying to compete with them, I'm trying to help the process by pushing things into manufacturing. So this gets us to, what is the SUNY Poly capability? I mean, I have it here at a fairly high level. We do have a complete 300 millimeter tool set. That means if I wanted to, I can build full CMOS chips. That's what that picture of me in the bunny suit was all about. It's 135,000 square feet of clean room. I mean, if you have a clean room at your university, typically you're an order of magnitude or so smaller. That size clean room is what you find in a normal scale commercial manufacturing line. There are giant factories that might be twice the size, but I mean, we're right there in the scale of what a manufacturing line would look like. There's a little picture of the inside of it. I mean, it is run by commercial entities. Most of SUNY Poly's revenue, in a sense, comes from industry. So we're, again, very unusual as far as universities go, in that the bulk of our revenue, or the bulk of the money that flows through us, is industrially based. And the processing capability, because it's 300 millimeter, we took a position that the earliest technology node that we're trying to support is 65 nanometer. The industry transitioned between 200 and 300 millimeter at that node. So there's a lot of companies that are today in the analog mixed signal space that will eventually migrate to 300 millimeter, at which point we are there to happily cooperate with them. And as you saw on that picture of me again, it can go down to 7 nanometer. That has now migrated to 5, the next CMOS node after 7. So we have the tool set. It is obviously state of the art. As the bullet on the bottom that says, because of the industrial partners on site, this tool set is continuously being upgraded. So it's not that it's sitting there and gets old. I mean, after some 7 years or so, typically tools will be removed and replaced by a newer model, which is somewhat of a problem if you're trying to maintain an old flow. So it's a mixed thing, but we're trying to do both in the same facility. We have been building silicon integrated photonics for the last 5 years or so, roughly in a very close collaboration with MIT, Mike Watts in particular, who designs a lot of the elements that we're building collaboratively between them. So between our two entities, it's like the fabless design house and the foundry, if you want to use that analogy in this case. Because we have 300 millimeter tools, I do not need things like OPC. I can use a commercial tool that has 193 nanometer wavelength for lithography and immersion machine. The resolution limit of these machines is about 42 or so nanometers without any additional help. So I can print without any optical enhancements features that most others would not be able to. Certainly 200 millimeter facilities cannot compete with that kind of tool set. And we do have a 3D process that we have developed over the years, 2.5 and 3D, so we can do die to wafer and wafer to wafer attach, and also incorporate CMOS into it if you wanted to. I think practically speaking, again, because of the environment of being an R&D line, we don't necessarily want to support CMOS. You're better off, if you ever think about that, go buy that from a foundry like TSMC. It's coming cheaper and faster than from us. So we are a member-driven consortium. So here's a set of logos of the companies that we're currently talking to. So we have no real members quite yet. Again, I'm a physicist, but my last 6 or so months I've spent as a lawyer, basically trying to get people to sign membership agreements. Given the kind of logos that I show there, both on the academic as well as on the industrial side, you shouldn't be surprised that this takes some time. I think I deserve either the Nobel Peace Prize or something like that after I'm done with this. The tiering of the academic, before anybody draws any wrong conclusions here, has more to do with how many PIs are involved. So I don't mean to imply that Berkeley is a tier 2 university. It's just that the involvement that they have with us is smaller than, say, the universities that you see there under tier 1. So we're in the process of finalizing the membership agreement. This is sort of squaring a circle because there are, as you might gather, mostly IP problems that people are concerned about, where positions are, basically being taken that have been taken for many years, that are difficult to get under one umbrella. Our legal structure is that we have a membership agreement that will be same for everybody, and then we have project award agreements. I'll get a little bit for how we're going about these things, but the project award agreements that are specific to the project on hand will be limited to 1 year and either renewed or replaced by something after that. So we are assuming that we get all this done by the middle of this year, after which you have to be a member if you want to be part of AIM Photonics. We also had the fortune that 3.5, maybe 4 states have pledged significant support. I think that was one of the criteria that allowed us to win this. In particular, the state of New York has pledged $250 million, a welcome addition, of course, as you might imagine. And the 2 states, California and Massachusetts, also pledged rather substantial amounts. Arizona a little less, but I'm obviously indebted to these states for providing that level of support. So let me get a little more into how this thing is going to work. As I said, no results yet, so don't hold your breath that I'm going to show you nice results. But here's how we're intending to get this done. We do have something that we ended up calling key technology manufacturing areas, and they're really representing industry segments. I mean, integrated photonics can make a difference in a number of areas. The one that you see on the very left, the datacom segment, is by far the most mature. If it had been only for that segment, I don't think integrated photonics would have been an NNMI, but it's more for the other 3. I think the industry is capable of pushing this along, maybe not at the same speed as what we can help them with, but certainly the datacom space is well established and well detailed. Analog RF is more of a military application space. The two on the right are, from my perspective, the more interesting ones in terms of the application spaces. One is phased arrays, think LiDAR, things of that nature. There are huge applications that have to do with the automotive space as well as the airline industry. And then the last one is sensors. Think in Internet of Things, if you like that nomenclature. Certainly sensors in general, if we can come up with a set of platforms that would support these, where we can help from a manufacturing technology perspective, define how something is to be built cost effectively, that's potentially the largest segment from a revenue perspective, because you've got healthcare, environmental, maybe agriculture as potential application sectors there. So, again, each of these segments has different industry partners that are interested in driving that, and that's an essential element of what we want. We want to help these companies. Then we have established these working groups. The nomenclature may have to change because that's being used by others as well, and not in the same meaning. But and again, these are composed of partners that are wanting to work with us, help us define what needs to happen in these areas. What does the industry want to see over time as a capability? And each of these working groups has, 3 entities being represented: an industry, a government, and an academic, and they're leading this as a triumvirate, then helping us making down selections on project proposals. And the idea of these things is that they're the drivers. So tell us what you need to see done, and we want to use projects like that to validate that what we're doing makes a difference. Again, manufacturing metrics. Is the cost better? Is it faster? Or whatever metric you're favoring here. So here's where most of the money will go. That is the infrastructure development in terms of our capability that's impeding why we can't do things faster or better at the moment. There are 4 elements. There's, of course, design automation. Today, it takes a PhD to do one of these designs. That's not a desirable outcome. The semiconductor industry doesn't operate like that anymore. It is very high level of abstraction. As a designer, you don't need to know what the foundry can do. It's all encoded within the software. So you can have the work performed by not as well-trained people, that also need to find jobs, and quite frankly, it lowers the cost of all these things. The biggest money sink, if you want to call it that, is of course the multi-project wafer infrastructure. That is the hardware built. It comes really in 2 pieces. It is listed there again as the next one down. There's test assembly and packaging, where today in the integrated photonic assembly, most of the money is. The cost of assembling such a piece to attach a fiber, for example, to whatever it is, your die or your module, is a very costly step because it's manual. That needs to be improved. So we're intending to populate some of that capability with new equipment. So a lot of the state investment, especially from the state of New York, will be used for that, to upgrade the capability that we have in Albany, mostly from a capacity perspective, so we can be faster and we can do more. But then the capability that we intend to put in the Rochester area, where we have 2 potential facilities, that we're intending to put these tools in. And the last one is inline test. This is one of those that, again, as a former semiconductor manufacturing person, surprises, but we don't have the ability to check on a product while it's being built whether it's any good. So the sad reality is that you're building these parts and you're relying on electrical correlations to the performance that the system has optically. And you really only know when you're done 3 or 4 months down the road whether you built the stuff well, right? That's totally unacceptable. You're exposing this much work in progress without knowing really what you're doing. So developing optical techniques that can make these measurements in the line while you're building it as often and as quickly as possible, so the time to detect of any deviations is minimal. That's a key manufacturing metric, and there's no commercially available tool in that space. People have, and this is fairly symptomatic for this industry, they've built their own solutions, and they're all homegrown. So there's companies that have specific, projects that they've done with some of these test suppliers, and the rest is a homegrown addition to it. Nothing is commercially available. It's a prime topic for us to hopefully help, create a publicly available solution that people can go off and buy. That's how the semiconductor space works. Right? The last one here is, of course, we do have a workforce element that I'll get to in a second as well. So how do we operate? If you've been in corporate America, it's not unusual. We do have a matrix structure. Again, back to here, the business segments, and here sort of the manufacturing infrastructure. We have two people that have key positions in this. I'll introduce them in a few minutes, the Chief Technology Officer and the Chief Operating Officer. These two folks coordinate these total 8 teams and make sure that, we, as it says there, have market-driven input. We validate whatever the manufacturing centers deliver, seek synergies. Of course, I would prefer not to have a unique solution for every one of these market segments. Some will unfortunately have to be. I don't think I can have a datacom solution serve a sensor in the biospace. But again, we'll look for at least as many synergies as we can. Coordinate the planning and the management, of course. And we are willing to consider if there's new segments, new business elements that we have not seen yet. I mean, this is the sort of thing that we're struggling with now. So I would be reluctant to add something, but I would expect that over time there will be some that we will add. So we also have a technology review board. I mean, I did talk about that a little bit already at some point when I said that there is individuals from the government, from industry, and from academia that help us run all these teams, each of the 8 teams. So these folks altogether, 24 of them, then are the technology review board. These are the folks that once proposals come in, help us to make a technical judgment on whether these projects are good, which one is the best, which helps us to have the biggest impact. It's more like publication review. I mean, it's not too dissimilar. Then it comes up to the executive team, and we put some additional filter on the projects, which has to do with sustainability. I didn't say that at the beginning, but all the NNMIs have been given a 5-year time horizon to become financially self-sufficient, sustainable, which in our case means a rather substantial amount of money on an annual basis. It's like, we're a well-funded startup. We've been given a lot of money, and the clock's ticking. Not a small challenge, because building a research infrastructure and an endeavor that people would want to come back with and pay for is a non-trivial challenge. So here's the near-term calendar, just to give you an idea where we are in the process at the moment. I mean, we kicked things off. So compared to a lot of the other institutes, from a timing perspective, we're actually doing very well. Most of the other institutes took over a year to get really established. We've done this in about 6 months, maybe a couple of weeks late compared to that internal target. And we have started to award projects. So as a number of these activities are already underway, a little bit at risk because we're not quite done with the contractual frameworks. But as I said, this should be done in the next few weeks. So in the meantime, we're looking for input into what we should be doing in 2017. And we're really trying to get this done more on a roadmap-based structure. Obviously, what we took, in order to get this done in about 6 months, we took our proposal that we submitted and we ran with it without getting additional input. So here's sort of catching up on that, saying, what's the roadmap telling us that we should be doing? So this is the process that's going on now. And if people are interested to get involved in this, I'll tell you in a second how to do that. But that's what's going to happen in the next couple months or so, then leading to another request for additional proposals down the road. Okay, so near-term capabilities. I just wanted to make sure that I show you in a very high level some of the capabilities, primarily listing at the moment what we have in SUNY Poly. We have ultimately the mission of providing multiple sources. So over time, there will be an indium phosphide-based MPW offering from Infinera. There will be a silicon-based offering from Orion, but the primary capability, silicon-based, will be out of SUNY Poly. You have here obviously list of things of photonic elements that we either have currently in place or are putting in place over the next few months, very much along the lines of what the semiconductor industry does, where you've designed this, you've proven functionality. But over time, you have to make sure that it can actually reproducibly be built in a silicon line. So there's a close collaboration again between the IP designer and the fabricator, where you need to make sure that you have defined it well enough you can basically trust that this will work. And timelines for this, we have 2 MPW1s planned for this year. They will be internal just to establish capability, but by early 2017 we expect to have a publicly available offering out there. We believe what we're offering will be a competitive pricing, about $2,000 a square millimeter, I think is for the kind of capability that we're offering here a reasonable price. That's what we're aiming at. Very briefly on educational workforce development, there's a whole set of activities there, ranging of course from arranging meetings that bring the community together, to MOOC platforms. Workforce development isn't just PhD level, by the way, obviously. I mean, it goes all the way from community colleges to PhDs. So we're trying to provide these based on industry demand. So there's a questionnaire out there to our industry members. What do you need and when do you need it? Please be specific so we can build the educational programs around this. A repository for stuff that has been done, and then we have an academic council that helps us, stay honest, I guess is the best answer. So the road mapping activities are an existing INEMI activity that we sort of merged with, or they merged into what we do. That activity was not 100% aligned to what we had, so we took the last 6 months to make sure that alignment is better. As you can see here from this picture, the new activities are RF analog and the arrays. The Internet of Things was narrowed down in scope a little bit to be more consistent with what we were doing, meaning sensors. So that really has to still bear fruit, but these groups are off and running, and they are now correlated very well with what we have internal to AIM in terms of the decision making. Now here's the roadmap, what do we take from that? So as you can see there at the bottom, AIM Photonics responsibilities take the open roadmap that's available to anybody. I would like to emphasize that we're not trying to be exclusive. The member component is then take that and distill it down to what our members really would like, and then decide on the most impactful of these projects to take forward. So how do you engage? Well, it's at the level of these working groups. There are 2, as I just alluded to. There's a roadmap element that's open to anybody. And then there is a AIM Photonics sub-element of this, where we're talking about selecting these projects that we then should ask for a call for proposal. These call for proposals are meant to go to members as well. Obviously, if you're paying a membership fee, you should be getting some benefit on there. But we're relatively open for people to join if they so choose and if they see an advantage in that. So as I said, it's not a closed community. It's just that it is a number of entities, both on the industrial and the academic side, that we've targeted first to talk to, on both sections here, on the KTMAs as well as on the MCEs. Here's the wanted ad. So you see the folks that are involved here. It's a very good group to work with. I mean, so we do have folks from UCSB, MIT and Arizona on the executive team. I would expect that over time, people want to, phase in and out of these. So again, it's not meant to be a forever, but it's the current set of folks that are managing our activities. So you have Mike Watts, the CTO. You have Doug Kuhlbauer from SUNY Poly, Mike from MIT. Doug Kuhlbauer from SUNY Poly being the COO. Kim Kimmerling for education and workforce development and the roadmaps. And then we have 2 outreach executives, really primarily on the industrial side of things, West Coast and East Coast, so Rod and Tino, who is a Sematech employee. And then Tom Koch does manage our technology review board. And the rest is staff, and then of course John Bowers. The nice way to say what he does is that if I get run over by a truck, then he is in charge. So. Okay, so contact, the easiest way, and that's the only thing you really have to remember of this whole thing if you want to get hold of us, just look us up, aimphotonics.com. One of the pages on our website has the contact names and the contact numbers and emails. So it's Tino and Rod that will be the first, to be harassed by you. Well, harass is the wrong word for this. Okay, so with that, I would like to wrap it up and maybe open it up for questions.